Right. Hello, Statistics 02260 students. It's Professor Barish, and basically giving you a little bit of a training, additional training on section 2.6 on linear regression. All right, just giving you some more details so that you can complete the homework and also feel comfortable when you take your test and also when you do your Excel project, which are coming up next week. All right, so I'm going to share the screen with you. And first thing I want to do is take a look at the textbook. And when we do regression, first thing we do is a scatter plot. We're comparing two quantitative variables to see if there is a relationship between the variables. And the variable that runs along the x-axis is called the explanatory variable. Variable that runs along the y-axis is called the response variable. Here's an example here that's in your book. And please do read the textbook because it does give you many examples and a very good explanation of all of this. But anyway, here's an example right here of a scatter plot. And this line here represents what's called the line of best fit or the regression line. Now, each of the dots here represents an XY point, the X point being the bill amount. In this case, the scenario is a restaurant bill. There's 157 restaurant bills here where you have the amount of the bill and the amount of the tip that was given to the waiter and waitress. Okay, so we want to see basically if there's any relationship between the size of the bill and the size of the tip that's given. And we see an upward trend, and this line here represents the line of best fit that fits all those. Okay, now the equation of a straight line should be familiar to you, right? It's all of you have taken 2 years of algebra, hopefully, when you were in high school. And one way of showing the equation is y hat is equal to b0 plus b1x. Now, b1 is the slope because that's the number that's multiplying the x or the explanatory variable x. b0 is the y-intercept, and y is an estimate of the or a prediction of the response variable. We put a little hat above it because this line is taking all the points into account, that it's on the scatter plot and coming up with a line that best fits all those points. And so the y is going to be an estimate of the y of the response variable for a particular value of the explanatory variable. This is another way of writing it right here, replacing the x with explanatory and the y with response. In the example we just saw, bill, the amount of the bill is your explanatory variable. It's running along the x-axis. And the estimated tip or the predicted tip is your y value. That's run along the y-axis. Slope is 0.182, and the y-intercept is negative 0.292. Okay? And you can make predictions with this. For example, if there's 157 data points in the data set, but if we come up with another billed amount, something other than what's in the data set, we want to predict from the billed amount what the tip would be, using that straight line as a way of predicting it. We simply replace the bill or the x variable with $59.33 multiplied by 1.182, and then add to it this negative 0.292 as a y-intercept, and that will give you the estimated tip. Okay, and that point, by the way, whatever that tip value is, will fall right on that line. Right? This is something you learned in algebra. That if you put an x into an equation and you get your y, that xy point is on that line. We're on that curve, whatever we're looking at. Same thing with the bill of $9.52. We plug it into the equation, replace the bill with 9.52 multiplied by 1.182, add to it negative 0.292, and we get our answer. So the book actually explains how to do this. All right, it's very easy. And since This type of algebra is a prerequisite for taking this course. I hope all of you know how to do this. Now, it is possible that you've been out of school for a while, high school for a while, and you forgot all of this. So it's really incumbent upon you to do a algebra review. That is, go to Khan Academy or some YouTube video and look and just listen to somebody talk about slope. That's not something that we'll do in this course. I mean, I'm trying to give you a little bit of a review here, but I don't really have, obviously, a lot of time because I'm supposed to be covering statistics and not algebra. So it's incumbent upon you, if you don't remember any of this and it seems kind of fuzzy to you, that you should do your own review, all right? Because otherwise, this becomes kind of confusing and maybe you don't do so well on your test because of the lack of memory of algebra, especially algebra about straight lines. All right, now that's the equation. That's called the equation of best fit. And I'll get to why that's called that in a few minutes. And then we have what's called the residual. Now the residual only can be calculated for the actual points in the data set. All right, I have to make that really clear. So all these, there's 157 in this particular data set. These dots here all represent these points. And so what we do is we choose an X that's in the data set. And for example, this point right here, if we choose the X, then the height from the X-axis all the way up to the point is the value of the Y coordinate, okay? So for example, if X is, let's say this is 27, then Y is maybe 2.4. So we would say that in the data set, there was one restaurant, or there's not one restaurant, one bill that had $27 for the bill, and the tip was $2.40. All right, that was what the person gave as a tip. Now, if we wanted to take that $27 there and make a prediction based off this line here, that's the line of best fit, and what we're really doing is we're calculating the Y value on that line, that point on the line. That it's not there right now, but it would be there if we actually had that value in the data set, at that point in the data set, that's on the line. In other words, what we would do is take the $27 bill and we would plug that 27 into the equation, all right, into the equation. So that equation, this equation up here, we would plug 27, replace bill with 27 and multiply by 0.182, add negative 0.292, and we would get our tip. Right? And that would be a predicted tip. That's not the actual tip. The actual tip is this height right here. This value here, the height of this, which is $2.40. But the line is going to predict something else. Right? Now, the difference between the observed amount, the observed Y value, all right, and the predicted Y value using the line, the difference between those two numbers is called the residual. It's like an error, right? The line is predicting one thing and the actual amount is something else. And we're looking strictly at the response variable here. So the observed is always first when we calculate the residual, and then we subtract the estimated Y after we plug in the X to that equation, all right? So a residual only exists for an observed value in the data set. If there's no observed value, there's no residual because there's no Y, all right? Then we're just strictly dealing with the prediction. But here for the actual 157 of these points in the data set, we can calculate a residual for each and every one of them. All right. So anyway, that's the whole idea of a residual. It's just the difference between the observed value and the predicted value for a particular X that is in your data set. All right. And that's what it means. All right, because they're going to bring out, in the section 2.6 homework, they do talk about residuals. I might actually, possible I can have an exam question on this. And by the way, anything that you read in the textbook, all right, is fair game for a test. It's not just what we review in class, because, it's only an hour and 15 minutes twice a week. There are other things that there's plenty of examples and things like that going on in your textbook. And I'm assuming that you're reading. All right. So if you don't read it, then you're missing out. All right. You're wasting a lot of time and not reading what you're supposed to be reading for this course. Okay. If you're depending strictly on what you see in class. So just know that, okay? Know that the things that are defined in the textbook, I'm going to try to get to most of them, but some things I won't get to necessarily. The textbook is very good, very clear, and you're responsible for reading it, all right? And you can always ask questions about what you're reading. But if you don't read the textbook, that it is a requirement for the course to read it. So then you're not doing what you're supposed to be doing, all right? So please read the textbook. Please do the homework. If you're not doing either one of those things, then it may be asking a lot for you to get a good grade in this course. It would be difficult to do that. Even if you come to every class, it's difficult to do that. All right, anyway, enough of that, enough preaching. And what I want to do next is deal with a particular data set. So I'm going to stop sharing here. And I've created an Excel spreadsheet sheet to show this data set. So I'm going to share again. Share. And go to Excel here. All right. Now this data set is called the election margin data set. It is one of the Excel spreadsheets that you can find in StatKey. Remember, that's where we go to look up our data sets. All the data sets in the book are there. And you can just download it onto your computer. And what you'll get is basically the first 5 columns here, A through E. Okay. I've added, by the way, in column C and column D, the parentheses here is for X and Y, because I wanted to make clear that what's in C is your explanatory variable, and what's in D is your response variable. Okay, so that's why I did that. Now, what is this spreadsheet for? Well, there are, I think there are 12. I think 12 here. Yeah, there are 12 U.S. presidents since 1940 that are listed here that were incumbent presidents, which means they were current presidents when they ran for re-election. So that's the name of these presidents: Franklin Roosevelt, Harry Truman, and so forth, all the way down to Barack Obama. This textbook didn't put in anything for Donald Trump. All right, and of course not for Joe Biden either. It's too recent. Column C is there just before the election, their, I guess, maybe final approval percentage. So, for example, Roosevelt, the people who were polled just before the election, 63% of the people polled approved of his job. The way he was doing his job, 62% approval rating. And D is the margin of victory of the actual election. Now, if it's positive, it means you won. If it's negative, it means you lost. And so 10 here represents 10 percentage point margin of victory. For example, if Roosevelt got 52% of the vote and his opponent got 42%, and 52 minus 42 is 10%, that would have been his margin of victory. All right. And so you can see the positives all are winning elections, negatives are all losing elections. So Carter lost 1980 to Ronald Reagan. George H.W. Bush, the first Bush, lost in 1992 to Bill Clinton. And then, of course, I missed Jimmy Carter here. Jimmy Carter lost to Reagan. No, actually, I did say that. I think the only one I missed was Ford. That's right. Gerald Ford lost to Jimmy Carter in 1976. All right, and then we don't have the loss of Donald Trump in 2020. That's not being shown. All right, so those are the data points. And if we did a scatter plot, this is what it would look like. Now, notice I have a line here that's part of the scatter plot, and that's one of the options when you create the scatter plot. So for example, if I click the scatter plot here and then do the plus, the trend line, if you see if I unclick it, that's the way it is. Typically, you just see the dots. You don't see the line. But if you click it and then click this here and go down to more options, you have options for different types of curves, but linear is the one we want. That, by the way, will give us the line of best fit or the regression line. And also, if you want to display the actual equation of the regression line right on the chart, you can click this one right here. You can see it shows up right here. All right, so I'm going to do that. Right, and then you can just take that equation, you can highlight it, and you can move it. Go here. See if I can move it. I'll move it right down here so it's easily seen. Okay. So what we see clearly is an upward trend, right? And the line, of course, is the best fitting line. Now I'm going to tell you why a line is the best fitting line in a couple of minutes. That's that one line that best fits that data. Now, what I created on the right here is number one, the slope and the y-intercept of that line. And in Excel, once again, I've showed this to you before, but you use the slope function, and the y values go first. That's the margin of victory column here, and then what comes out, and then you have a comma, and then the column after that is our approval rating. So you put your y or your response variable in first, and then your x or explanatory variable in second when you create your function. And there's your slope. Now I rounded it to 3 decimal places. You can see in here, they rounded it to 4 decimal places. And then the intercept, we use the intercept function and do the same thing, where the y variable or the response variable is first, the explanatory variable or the x variable comes second. All right, and that of course matches what you see in the graph. That's our equation. All right, slope and intercept of that equation. Now, the question, of course, is why do we use this line as opposed to any other line that you could possibly draw through those points? And the reason is that we want to find that line that minimizes the distance or the residual distance between the point and the line. All right, residual distance. All right, so I'm going to stop sharing just for a minute. I want to go into the residual idea a little bit more, and then come back here. Right, so I'm going to share again, and I'm going to share with you a PDF that I've created. It has 2 different concepts in it. One of them is the interpretation of the slope, which is the page 1 of this handout, and I posted this on Canvas. And then page 2 is something residual. So we know how to calculate the residual. It's the y, observed y, minus the predicted y from the line. And what we notice is that if a point is actually above the line, then it will have a positive residual. That's because its height. You look at this example here. If you look at when x is equal to x1 here, notice that the observed is higher, that the height is higher for the point than for the line, right? If we just run our cursor up here and get to the line, you notice that that estimated y there is going to be less than the actual y here. So we should have a positive residual, y1 minus the estimated y1 would be positive. On the other hand, if we have a point that's below the line, we should have a negative residual. And that's because the height going from the x-axis at x is equal to x2, going up to the point, notice that that height is lower than the height if we went all the way up to the line. So the y2 is less than the estimated y2 that's on the line. Therefore, y2 minus y2 hat, which is the estimated y, is going to be negative. All right, so that's the general rule. Now, if the point happens to be on the line, the residual is 0. All right. Okay. Now, if we have, this is the equation for this line here. This is just a hypothetical line with a slope of m and the y-intercept of b. Using y hat here because we're using the line to predict or estimate the value of y for a particular value of x. Okay, and this point will fall on that line. Now, if we have x1 as our explanatory variable value, x1, we plug that into our equation here, we're going to get our estimated y to be y1 hat is equal to slope times x1 plus the y-intercept. So this will come out to a number. And the same thing with x is equal to x2. I will be estimating what's called y2 hat, which is the estimated y on the line, and we plug in x2. Okay. Now, the residuals for the first point will be y1 minus y hat 1. Notice that I'm going to create an equation here, and I'm replacing y1 hat with the right side of that equation, mx1 plus b. All right. Same thing with the second residual, using the second point, replacing the y2 hat with mx2 plus b. Now, this is where I want to show to you something very important. I want to show you how to calculate the residual, right? If that's a question on the test. So let's do let's actually put some numbers in. So for example, if x1, y1 is actually 2, 6, that's x is equal to 2 and y is 6. And the second point is where x2, y2 is equal to 5, 4, where x2 is 5 and y2 is 4. Suppose the regression line is y hat is equal to 0.5x plus 3.5. 0.5 is your slope, 3.5 is your y-intercept. So what would be the residual for this point? Well, we know that y1, the actual observed y, is 6. And what is y1 hat? Well, that's this equation in here. That's the slope times the x1 hat, that's 2, plus the y-intercept. So if you multiply these two numbers here, you get 1, and you add it to 3.5, you get 4.5. So what's inside the brackets here is 4.5, and you subtract that from 6, you get a positive 1.5. Here's your positive residual. Do the same thing for the second point, where x2 is 5 and y2 is 4. So we know that the actual value of y is 4 minus, and then we put in our estimated y as the equation of the line. Then we're saying again the slope times the x value, which in this case is 5, plus 3.5. So 5 times 0.5 is 2.5, plus 3.5 is 6. 4 minus 6 is -2. So -2 is your residual. All right, so that's just shows you exactly how to calculate residuals. Stop sharing, go back now to our spreadsheet. Now, what I did with the Excel spreadsheet is, in this column H, is I calculated the predicted margin. The predicted margin of victory. That's the y value, right? That's the y hat. How did I do that? I simply, let's look at the equation here. I simply took G2, which is the slope, right? And I multiplied it by what? C3. What's C3? Well, that's the x value. That's 62 in this case. And added the G3, which is the y-intercept. That's the equation to the line. When I do that, I get 15.234. Right? So the actual margin of victory for Franklin Roosevelt was 10, but the predicted margin of victory based on the equation of the line is 15.234. If we subtract those two numbers, 10 minus 15.234, we get minus 5.234. Okay, that's what we get. And that is our residual. And that's what I did for each of these cases. Some residuals are negative, some are positive. Notice that when I add all these residuals up, every single one of them that's in the data set, it always comes out to 0. All right. Now, if it doesn't come out to 0, it's just rounded to 0. And when I round to 3 decimal points, it's just 0. Okay. And that's true for any data set. Any data set where we're calculating residuals from a scatter plot. When we calculate each residual and add them up, it always adds up to 0. Well, that's a little bit of a problem if we want to use the residual to determine what the line of best fit is. So what the statisticians have decided to do, they always come up with ways of doing things, is they decided to square the residuals. So in this column K, I'm just taking what's in J and I'm squaring each of the numbers in the data sets. Each of the residuals gets squared. Notice that the negatives become positives when you do that. And then when you add up the residuals, you just happen to get this number here, 320.417. Now, here is the real definition of the line of best fit or the regression line. It is the one line out of all possible lines which has the smallest sum of the residuals, the sum of the residuals squared. So this column here, this number here, if we did this for any other possible line that we could draw through these points, this would have the smallest sum of the residuals squared. 320.417 would be the smallest number. And that is how a statistician select the line of best fit. Okay. Now, how do they determine what the smallest value should be? They use calculus to do this. And it's easy to do it with calculus if you know how to use calculus. This course doesn't use calculus, it uses very basic algebra. So we're not going to show you how that works. But just believe that the people who programmed the Microsoft Excel, the people who programmed your calculator have put that calculus in there so that it always calculates the proper line of best fit. All right, so I wrote this down in red here. Of all the possible lines drawn through the scatter plot points, the regression line has the smallest sum of the residual square, this number. All right, so now we know what the line of best fit is, why it was chosen. The question is, how do we use it? Well, we use it to make predictions. We want to make predictions for values of X, the explanatory variable, that are not in the data set. Now, it's very important that when we make these predictions, we always make them for values of X that are in the range of actual values in the data set. Because when we calculate these residuals, we're using the actual X values in the data set. And those X values have a minimum value and they have a maximum value. So if we look at all the X's here, we see the maximum value is 70 and the minimum value is 31. So when we make predictions using values of X, the explanatory variable, we must choose numbers in between the smallest number here of 31, in this case, and the largest number 7, because that's the biggest number. If we try to use predictions, we try to find predictions using values of X that are smaller than 31 or bigger than 70. We can't use this method because this line here was based on just these points here. So to go outside the range of X to something smaller than 31 or bigger than 70, it's possible that this line of best fit doesn't work for those points. So that's important to know that sometimes there's a question on a test or homework which is related to that idea. All right, we never go outside that range of the data set. Okay, so all the values of X that I'm using here, which are not in the data set, are all within that range. I'm using 42% for an approval rating, 45%, 52, 58, and 65. And since these are not in the data set, we have to use the line as the way of predicting the margin of victory, right? We're using that slope and y-intercept. So basically, we take the value of x here, and we plug it into the equation. And in this case, if the approval rating, hypothetical approval rating is 42%, we would predict that this person would lose the election by about 1.5 percentage points. If the president or incumbent president had an approval rating of 45%, we would predict a victory, a narrow victory, a little bit less than 1%. 52% also would be a victory, a bigger victory. If they had a 58% approval rating, even a much bigger victory, 65, of course, much bigger than that. All right. So this is a way of making predictions using the line of best fit, and that's the purpose of it. All right. So hopefully you understand better what a residual is, how we use it in determining the line of best fit. And once again, technology, the Excel spreadsheet itself and the calculator know how to find the line of best fit. You don't have to do any sort of, use any sort of formulas or calculus or anything like that. It does it for you. It's really easy, right? So the line of best fit is something you just figure out and look it up. That's all you're doing, all right? You're not doing any math. All right. Now, this is how we use it, do this in Excel, all right? Now, the residuals and the sum of the residuals, you know, I use that for illustration purposes, but if I wanted you to do this as part of an Excel project, or Excel quiz, you have this spreadsheet here as a template. So you just use the template and recreate it for a new data set, just like you do for any Excel spreadsheet that I'm posting for you. All right, so that's it with that. I do want to stop sharing this, go back to that handout. I want to say one more thing here about the slope of the regression line. So actually, let me actually share with you again. Share. And I'm going to share that. There we go. Now sharing with you the handout, first page of the handout, the interpretation of the slope of the linear regression line. Now, in the homework, there's a couple homework questions that deal with this, so this is why I wanted to go over it with you. Some of you probably already knew this when you took your classes in algebra in high school. Maybe some of you don't remember this at all. So once again, I'm recreating the equation that we just saw from that from those presidential elections, all right? That this is the slope and y-intercept again. So this is our prediction line, our regression line for that situation. When A39 is the slope, negative 36.760 is the y-intercept. X, once again, is your explanatory variable. Y hat is the predicted response variable. Remember, we're using this equation for predictions. So what I'm doing here is just going through a little bit of algebra to explain to you how the interpretation of slope works, all right, in this context of linear regression. So suppose we have 2 points that are on this line here, on the line, and we can call one of them x1 comma y hat 1. Now remember, this is a y that's on the line, all right, on the prediction line. So we're using for the y the predicted value of y. And the same thing, we have another point x2 y hat 2, right? Now we could determine the difference in the y values. For example, y hat 2 minus y hat 1 between these 2 points is really the vertical difference between the heights of those 2 points. We could call it the change in the value of y, the predicted change of the response variable. Similarly, we can subtract x2 and x1, which would be the difference in the x values of these 2 points, all right? And that would be the change in the explanatory variable. Now, the slope in general is, in the numerator would be this is rise over run. This is the change in y divided by the change in x. Okay. But I'm going to go through a different route here just to show you how we come up with an interpretation. So we have this one point here, x2, y hat 2, and if we happen to plug that into the equation, we would get this. So we just take our y hat 2 and plug it in for y hat, and take the x2 and plug it in for x. We do the same thing for y hat 1 and x with this first one, x1 and y hat. All right, so we have the same equation, but with two different points just plugged in. Suppose we want to calculate the change in the y value, the predicted value of the response variable. So we simply subtract these two, right? y2 minus y1, that's the change in y. And we're simply replacing the y2 hat and y1 hat with the right side of each equation here. Just replace them here and here. And then what I'm doing is I'm literally just rearranging terms, right? This negative here for the second term, we'll just distribute the negative across. And then rearrange the terms, and we put our x terms in one set of parentheses, and we put our y-intercepts in the other. And so notice that both of the terms that have the slope in them, okay, notice that we can just simply factor out the slope, and we end up with x2 minus x1, this term here. And then when we add these two numbers up, obviously they go to 0, because we're literally subtracting the slopes, the y-intercepts. So the y-intercepts simply will disappear, will cancel each other out when we subtract them, when we subtract the two equations. Y-intercepts disappear. And so what we end up with is that the change in y, the predicted value of y, is equal to the slope times the predicted value of x. Now, you will notice that if you divided both sides by the change in x, here, this x2 minus x1, you would get the slope on the left equal to 0.839. Right? This is just another way of showing the same thing. So the point here is we can have an interpretation using the slope. What we do basically is say the following. Suppose we say that the change in the explanatory variable is positive 1. That is, x2 minus x1 is equal to 1. 1 unit of the explanatory variable is increasing. The explanatory variable is increasing by 1 unit. Right? So if we say that, well, we're going to say x2 minus x1 is 1. We plug it into our this equation here. We're replacing x2 minus x1 is with 1, and then we know 0.839 times 1 is 0.9. So y hat becomes 0.839. Or excuse me, the change in y hat, not y hat, the change in y hat, the y2 minus y1 hat, this here, is equal to the slope. So what does that mean? That means that if the explanatory variable increases by 1 unit, whatever that unit is, in this case it's percentage points, of victory, then the predicted response variable, the change in y, increases in this case by 0.839. Right? Why does we say increase? Because it's positive. The slope's positive. Okay. So anytime we're increasing x by 1 unit, we're going to increase the y value by the slope if it's positive. Now, if the slope happens to be negative, we would say the opposite. We would say as we increase x by 1, then we would decrease by the value of the slope if the slope happens to be a negative number. Make sense? So here's in general, this is the general truth of all of this. When we increase the explanatory variable by 1 unit, the predicted response variable increases by the value of the slope. And you will see examples of this in the homework. There'll be statements that basically say that. And whenever they show that statement, and they'll say, well, what is this representing? The answer is slope. They're going to give you choices like the correlation, the y-intercept, the slope, of course, would be one of the choices, and some other things. And just know, number one, that if you make a statement like this, it has nothing to do with the correlation, that number of the correlation. Remember, correlation runs from -1 to 1. It's unitless. It has nothing to do with it's not talking about the slope. It's talking about the strength and direction of the linear relationship. So it's going to be between -1 and 1. If it's a positive relationship, and basically if the number is close to +1, it's less than +1, but very close to it, we would say a strong relationship. If the trend is downward, the correlation's negative, and it's close to -1, we said it's a strong negative correlation. Or if it's very weak, if it's close to 0, we would say there seems to be no correlation or no relationship between variables. But that the correlation itself is not something we can interpret other than to say strength and direction. That's all it is for. So if you see anything like what I just talked about, that has to do with slope. Can't be the y-intercept, because remember, when we subtracted y2 minus y1, the y-intercepts cancel out, turn to 0. So it's nothing to do with the y-intercept. All it has everything to do with the slope. All right, so just know that this is a algebraic proof of this interpretation. Right now, some of you who like math might like this proof. Some of you who don't like math so much, this may be something you're not really interested in, but just know this is the reason why that interpretation is the slope. Okay. The final thing I want to do today is look at the calculator. So let me see if I can see the calculator here. Here we go. We'll share the calculator. All right. Now, what I have already done is that when I hit stat and hit enter, notice I put my X variable, my approval rating percentages, in L1. And there's 12 of them. I likewise put in the margin of victory percentages in L2. Now, and you can put it in any order you want, but I like putting X in first and Y in second, because that's the way calculator typically defaults to. It defaults to L1 for the X and L2 for the Y. But again, it doesn't matter which order you put it in, as long as when they ask what list is the X variable, you put in the proper list. The same thing for the Y variable. All right, so now we have this set up. And what we want to do is, number one, we want to find that equation. All right, so hit stat. And again, we scroll over the calc. And option number 4 is LinReg for linear regression. So I'm just going to 4. And notice again, it defaults, the X list defaults to L1. Well, the X's are in L1, so I don't need to change that. And the Y list that defaults in L2, and the Y's are in L2. So I'm good. Now, if I go all the way down. Now, by the way, if you have an 83 calculator, you won't see this on your screen. You're going to basically, it's going to be sort of like a blank screen, and you're going to be putting, what you're going to do is you're going to type in using second 1 for L1. You're going to do second 1, comma, second 2, because it's going to ask for the X list first, X variable list first, and then comma, the Y variable list second, and then hit enter, right? In this case, for those of you who have the 84 calculator, this is what you're going to see. Now notice that in this screen here, the only thing I see is the regression equation, and then what A, the slope is, and what B, the y-intercept is. These match, of course, what we've seen in the Excel spreadsheet, right? And also in the scatter plot in Excel. This perfectly matches it. One thing is that it's not being shown here is the correlation coefficient, which of course you will need to also know, both the test and the Excel project that you'll be working on. So since it's not on the screen here, how do we put it on the screen? I did demonstrate this in class, but I'll show it to you again. You need to go to the catalog in the calculator. You go second 0, where the catalog is, and then you just simply scroll down until you get to the D's. These are in alphabetical order. And then what we're looking for is diagnostic on. All right, we just went past it. So the arrow, we want that arrow to be next to diagnostic on. We hit enter again. If you hit enter twice. Now if we go back to stat, again, scroll over to calc and choose option 4. And then scroll down so we get the calculate and hit enter. Notice that the correlation coefficient shows up as the very last number on the screen. Now this R squared here, ignore it. It's not used in the first semester of statistics. We will, if you take a second semester, then you'll learn about what R squared means. All right, something separate. But it is the square of R. It's just not being used in this course. So ignore that. Just use R. Right. So if you're asking for the correlation coefficient, use this last number here, 0.8639 is the correlation coefficient, a strong positive trend, right? All right, and that's a linear trend. Yeah. All right, now the equation again is y is equal to mx plus b, and then this is your equation. All right, so that you find the equation this way. You can make predictions. Now the predictions you have to take some pencil and paper and write down the equation. All right, you replace the a with this number. You replace the b up here with this number, and that's your equation. That's your y hat. All right, they don't show y hat, but it's a y hat. Okay, and then for a particular value of x, to find the expected or predicted value, you simply plug in that value of x into this equation and multiply it by the slope, which is in this case 0.8386, and add to it the y-intercept, which is negative 36.76, and you get your predicted value of y. That's your y hat. All right, so just use your calculator to do that. Okay. Now, how do you create a scatter plot? How do you create a scatter plot here? One thing I do want to do, let me just write this equation down for a second, because I do want to show you something that's kind of interesting with the calculator. Okay. All right, suppose we want to display the scatter plot. How do we do that? We go to second. First of all, you want to set up a window. Right? You want to set up a window. I didn't really do that. Let's set up the. So give me a second here. I'm getting a little. There we go. Here we go. Here's our window. Now remember the x's. If we go back, let's actually stop share. Well, actually, one thing we could do here, this would actually be helpful, is to set up a window. We want to make sure our scatter plot can be seen. Remember, we want to make sure the x's can be seen, the y's can be seen. And so one way of doing this, by the way, a quick way with your calculator to know what the range of x's are and the range of y's. We're going to go back to stat, and we're going to scroll over and notice that we do have a choice number 2 here, which is called 2 variable statistics. So this might be useful in this case to use 2 variable statistics, which will give us both the x and the y statistics. So let's actually choose that. We're going to scroll down and choose 2. Hit enter. Once again, the x list we know is in L1, the y list is in L2. And we'll just scroll down, hit enter. And notice it gives us statistics both for the x and the y. Now, in this case here, I'm just interested in the minimum values for x and y. So notice they're given at the very end of this list. And notice that x runs from 31 to 70, and y runs from negative 9.7 to 23.2. Now, I already came up with something that a number for x, the smallest number of x, something a little bit smaller than 31. So the maximum something a little bit bigger than 70, and the same thing with the y's. Something a little smaller than negative 9.7, something a little bit bigger than 23.2. That way we can easily see all the data in the data set. So if we go back to the window, you can see I chose x minimum from 20. We want a minimum for x to run from 20 to 80. Again, you can choose whatever numbers you want. Just make sure that the minimum here is something a little smaller than the minimum value of x, and the maximum value of x you choose is something a little bit bigger than the maximum value of x in the data set. I'm choosing a scale, x scale of 5, just because I don't want the notches too close to each other. And it seems reasonable that the notches should be 5 units apart if we're running from 20 to 80. Y minimum, I'm choosing -20, Y maximum 30. Again, for the same reasons I said before, you can choose whatever you want as long as the Y minimum is smaller than the smallest Y of Y in your data set, and Y maximum is something a little bit bigger than the biggest number of Y in your data set. I chose -20 to 30. And again, I use Y scale 5, just it seemed reasonable to use that. And then if I do and then of course, I'm going to make sure I go to stat plot. Notice my stat plot's already on because I've used it before. All right, hit enter. And again, it's highlighted on, which is good. And I scroll down to type. And notice the type is the scatter plot that's already chosen. The X list is in L1, the Y list is in L2. So if I hit graph, there's my scatter plot, and all 12 of those values are here. This one in the middle here is 2 that are to be on top of each other. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 of them. And you can use the trace button again to, it'll actually highlight one of them. Actually, it'll highlight the ones that you put in order. All right, so the 62, the approval rate of 62, this was the Roosevelt one, and the margin of victory of 10 for Roosevelt, that's this point here, and then you can simply just use your arrow button to take you to the next one. All right, and the next one, and the next one, and the next one. All right. Okay, so that's my scatter plot. Now, what's kind of interesting here is if you do want to draw the line of best fit through this scatter plot, if that's something you would like to do. Now, one thing you could do is go back, actually go to the Y is equal to button here. It's a button you used when you were doing algebra and put equations in. And if you go to Y equal to and actually type in the line of best fit. So I put in 0.8386 times X. Now, where do I put the what button do I use for the X? Well, there's a button right next to the alpha button here that says X, comma, T, and then it's stated and some other things here. Use that because it'll choose X for you. And then plus put in your Y-intercept, which is 36.76. All right, and there's your equation. Now, what's going to happen is if you hit the graph button, look what happens. You get your scatter plot. And oops, looks like it didn't work. I don't know why it didn't work. So I'm going to go back to Y is equal to. Oh, I see the problem. Notice that the equal sign is highlighted here. So if I hit the enter key there, let's see what happens. I believe that when it's highlighted, it doesn't display it as a graph. So now it's not highlighted because I hit it my enter key, and let's see if that works. Work. Of course, I'm recording this. So let me see what the issue could be here. So maybe it should be highlighted. Let's go back and highlight the equal to sign. See if that makes a difference. And then we'll just bring the cursor down. All right, let's try graphing now. Still doesn't work. And I'll try one more thing. Otherwise, I'll just say forget it. Because I did do this before. And it did work. So maybe if I unhighlight the equal sign, scroll down, there's my equation, 0.8386 times X plus 36.76. All right. And if I hit graph, see if that works. And for some reason, it did not work. So it did work for me before. So what ends up happening when it does work is that the line actually goes right through the point. So you can actually get the line that best fit in there. But for whatever reason, it is not working. And I'm a little shocked because it did work earlier in the day. So not quite clear why it's not working here. Don't worry about it. It's not something you have to do on your calculator. Now, of course, I might ask you to do this in the Excel spreadsheet. So that you do know how to do that now with Excel. It's easy. Excel should never have an issue with drawing the regression line through a scatter plot. So should be able to do it. Here, it doesn't seem to work. So I'm just going to actually read all of this. All right. And I think my calculator is acting a little weird here. So, so forget about what I wanted to show you there. It didn't work, but again, it doesn't need to work because with your calculator, the only thing that you will be using it for is to find the line of best fit, that regression line. You're going to use your calculator to find the correlation coefficient. You're going to use your calculator to calculate your predictions using the regression line. And also, you'll be able to also calculate residuals. So you'll be able to do all of that with your calculator. And there's no need to draw a scatter plot or even draw the line through the scatter plot. The only usefulness of the scatter plot is so that you can just visualize the actual trend. You can see what the trend would be. And then when you determine the correlation, you can see whether it matches what you thought the trend should be, whether it's upward sloping or downward sloping or a zero trend. All right, so that is it. I think I'm done. Stop sharing. And that is it for tonight. So I'm going to go ahead and post this. I'm going to record it, not record it, I'm going to get this recording completed and post it. And of course, the fact that you're actually seeing this means it's already been done. All right, so silly to say that. All right, so that's it. And that is an additional review of section 2.6. Hopefully it was helpful and you'll be able to do your homework successfully and also do the test successfully and the Excel project, the Excel quiz successfully. All right, so have a good night. See you later.